back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, every week we profile some of the most amazing developments in science. We're talking about profiling the breakthroughs that are changing the way we view the universe and also affecting our daily life. Well, on Science Fantastic, we've had Nobel Prize winners, directors of major laboratories, talking about the creation of the universe, about the possibility of time travel, antimatter, dark matter, the cutting edge of science. But today, we're going to take a step in a different direction. We're going to talk about the physics of everyday things. That's right. I wondered, how does a laser work? Or what about stealth bombers? How do they work? Not to mention, how do we know where the moon came from? Or how do we know how old the dinosaurs were? Things that we encounter every day, but leave us with our heads scratching, wondering, how do they do that? How do they calculate the age of a dinosaur? How do they know where the moon came from? Well, with us today is someone who's going to explain the physics of everyday things. The book is called The Physics Behind ... So in other words, we are going to talk about the physics of everyday life. With us today is Russ Swan, author of the book, The Physics Behind, and we got him all the way from England. And so once again, we're going to be talking about the things that have your head scratching every day. How does the touch screen work? What is Moore's law? How do stealth bombers work? How do we know where the moon came from? How old are the dinosaurs? And how do we know? These are some of the things we're going to be talking to Mr. Swan. So Russ, glad you could join us all the way from England to get on Science Fantastic.
It's a real pleasure to be here, Dr. Kaku.
Okay, well, first question is, why do you decide to write a book about the physics of, ordinary things that puzzle us every day? Why did you decide to write this book?
Well, it's more or less what you've already described. Everything that happens in everyday life has some science behind it, and in most cases, that science is actually physics, because physics is kind of the fundamental science that drives everything that we do. And as life gets more complicated, we have more and more technology involved in everything that we do. It seems to me that actually we're losing touch with the basic principles and the basic phenomena that are behind all of the things that we do. And it just seemed to me that there was a lot of things there to say that perhaps people would be interested in learning a bit about. And so the opportunity for the book came up, and there we are. It seemed like a good idea at the time.
Okay, well, people come up to me and say, Professor, you're a physicist. I mean, what does a physicist do anyway? Well, we invent things. We invented the transistor, which makes possible the computer. We invented the laser, which makes possible the internet. We wrote the World Wide Web. And not to mention that in a hospital, we invented the X-ray machine and the MRI scan. In everyday life, we invented television, radio, microwaves, radar. We also invented the space program, which was all done by physicists. We created the GPS satellite. So what do? Well, we invented most of the 21st century.
Indeed.
So let's get right into the substance of your book. Your book mentions, of course, computers and touch screens. So let me ask you a question about Moore's law, which you mentioned in your book. What is it, and why does computer power advance so rapidly?
Well, that's a really interesting question. And of course, Moore's law is the law that states that, roughly speaking, computer power doubles about every 2 years, 18 months to 2 years. And it was a law that was first described in 1965 by a chap called Gordon Moore, who really noticed that he was getting twice as many transistors onto a chip about every 2 years. And so he extrapolated that forward, saying, I wonder if this will continue. In fact, when he described it, he didn't state it as a law. It's since been considered to be a law. But he made it really an observation. And since then, it's remarkable that 53 years later, the pattern has stayed really very accurate, that about every 18 months to 2 years, you can get twice as many transistors on a chip. And, of course, twice as many transistors means that you can do twice as much computing, twice as much processing. So it's one of those things that we don't really know whether it would have continued in that pattern had Gordon Moore not described the law, or whether it's continued in that pattern because he described it and people thought, we have to do twice as many to keep up. Otherwise, our competitors will be doing twice as many. Interesting, but the miniaturization involved, of course, gets harder and harder each iteration, each cycle. It gets harder. The first time it's half the size, the second time it's a quarter, and so on.
Right. And isn't that done using, well, ultraviolet radiation and etching technology, similar to how we make a T-shirt, by etching tinier and tinier transistors on a silicon chip? So how does that work?
Well, this is where the lasers come into, of course, because the etching process used in what are called the fabs, the fabrication facilities, they use smaller and smaller wavelengths of laser light, because then you can focus to a smaller and smaller dot. And there's a parallel here with things like optical discs, where you have a CD and then a DVD and then a Blu-ray, and each of those uses a smaller laser dot in order to get more information onto the same size of disc.
Okay, now, I remember when I was in high school, when the first computers were being made at Stanford and other universities, it was so painful. It was so painful putting input into the computer. You had to use punch cards. You had to type it in, make a mistake, and it bounces right back. Now we have touch screens. You just touch the screen, and instantly it does magic. So how does a touch screen work?
Well, as you're probably aware, there are more than one type of touchscreen. And there are capacitive touchscreens and resistive touchscreens, which are the two main types used in things like smartphones and iPads and so forth. And the capacitive touchscreen is very clever. It uses a trick of your finger, which is why it doesn't work when you put on a piece of plastic or a piece of paper. It relies on the electrical conductivity of your fingertip and can measure really quite precisely where that is touching onto the screen and translate that through some very clever processing system to give it the XY coordinates of the point on the screen where you are touching and give it a clue as to what you want it to do.
Welcome back to Science Fantastic with Professor Michio Kaku. Today, we're not going to talk about the physics of time travel or the physics of space warps or wormholes or higher dimensions or anything like that. Today, we're going to talk about, well, the physics of everyday things. Lasers, computers, touchscreens. And we're going to talk about, well, outer space, the origin of the moon. What is dark matter? What is the standard model of physics? With us today is Mr. Russ Swan, author of the book, The Physics Behind. And we are going to talk about the physics of, well, ordinary things. Well, we talked about Moore's Law, which simply says that computer power doubles every 18 months. And we get Moore's Law because we can etch tinier and tinier transistors using laser light or ultraviolet radiation. But then the question is, well, what is laser light? So, Russ, tell us why laser light is so different from ordinary light.
Well, laser light is made of exactly the same stuff as ordinary light. It's made of photons, which are really tiny packets of energy, the quanta of energy. But the difference between ordinary light, which has a whole load of wavelengths and a whole load of different colors because of those wavelengths, is that in a laser source, all the photons, all the quanta of energy are the same energy. They have the same color and the same wavelength, and so they appear as just a single color. You cannot have, for instance, a white laser. That's sort of a physical impossibility. But you can have a red laser or a green laser or a blue laser as long as it's at that one single wavelength. And the other thing that a laser light has, besides being a single wavelength, is what we physicists call coherence. And it means that all of the wavelengths, all of the quanta of energy, the photons, are vibrating at the same time. They're sort of dancing around together, and they go up together, and they go down together, and they vibrate in exactly the same pattern. So this means that you can take a laser light, you can do really interesting things with it, but things you cannot do with a regular light bulb from a call them very sharp cutoff, very sharp startup. And lasers are still producing some of the most interesting technological breakthroughs that we're getting in society today. In fact, the 2018 Nobel Prize was announced quite recently, and the winners of that prize, there were 3 of them altogether, were all working with laser light.
And according to the press release, one of the applications of this was to create optical tweezers, the ability to manipulate tinier and tinier things, just as if you manipulate tools. Could you explain?
Well, optical tweezers are a bit like, if you've ever watched Star Trek, the science fiction program, it's the tractor beam from Star Trek. It means you can use a laser source and you can control it in a certain way so you get what they call a wasted beam. And that can catch and move around tiny objects, tiny things like bacteria can be captured by a laser beam, just like a tractor beam, on a very, very small scale, of course. And they can then be used and studied to see what they're doing. In fact, optical tweezers have become, in biology, one of the most powerful tools of the last couple of decades.
And do you think that one day we'll be able to create tractor beams like in Star Trek? Is that a possibility, or is that strictly science fiction?
Well, I honestly think you can never say never. It is science fiction today. I don't think anybody has any serious proposals to make a tractor beam that could capture a spaceship. But, in 100 years, in 200 years, who's to say?
Okay, and talking about light, of course, one of the most fascinating things that children notice is the rainbow. We think we know a little bit about rainbows, but tell us a little bit about how rainbows actually are formed.
Well, rainbows are really still quite magical. And, where I live in the UK, in England, we have weather that means that it's sometimes rainy and it's sometimes sunny, and that means we get more rainbows than other places in the world will get. And you've seen a rainbow. You know how they appear to move with you when you walk around. You know about the myth of the pot of gold that can be found at the end of the rainbow. And the fact is, the pot of gold at the end of the rainbow might be there because nobody's ever been to the end of a rainbow. It's impossible to get there. The rainbow is an everyday thing that when you're a child, you think, wow, what on earth is happening? And as an adult, we tend to think, oh, well, it's just a rainbow. It's pretty, but nothing special. But it is kind of special. It's the light from the sun being refracted through the raindrops that are suspended in the atmosphere. And it's the same effect as if you look at a CD or a DVD disc and you get the kind of rainbow shimmer. The different wavelengths of light are bent backwards towards you by a different amount depending on their wavelength, on how long they are. And there's some really interesting things, some interesting facts about a rainbow. A rainbow is always down from the sun. So if you could see your own shadow, as you sometimes can, your head is always the center of the circle of the rainbow. And if the sun is really high in the sky, it can be too high for a rainbow to form. But when it goes down, the rainbow goes up. And if you get a rainbow at sunset, as I saw actually just a few weeks ago, the rainbow is a complete semicircle, complete in the sky. Because of this effect, it's what we call the 42-degree rule, that the line from your head to the side to the edge of the rainbow is always about 42 degrees.
Right. Now, if you take a look at the origin of why light bends when it goes through glass or droplets of water in the air, you go all the way back to Isaac Newton. It was Isaac Newton who showed that white light is actually composed of different colors, but the fact that these colors bend at different rates inside glass, isn't that due to the fact that different colors travel effectively in glass at different speeds? So since the speed of light in glass is not a constant, you can have different colors traveling at different velocities, and that's the reason why white light bends into all the colors of the rainbow, right?
That's exactly right, of course. And as the light bends by different amounts, the colors become separated, and when they then fall into your eye, you can see the different colors in different places in the sky. Of course, Newton's great genius was not just splitting the light into the different colors. He then recombined it back into white light, which was the thing that really proved that it was white light split into colors and then recombined back into white.
And by the way, even though we don't get into the biology of colors, isn't it true that the human eyeball cannot really see all the colors of the rainbow at all? Only 3 colors, red, green, and blue. And it's sort of like an optical illusion that we think we're seeing all the colors of the rainbow in their true form, but we're only seeing combinations of 3 colors, right?
Well, this is the same way that a television screen or your computer monitor works. It builds up a complete range of millions of colors using the primary colors. It's quite a clever technique that has been developed really by nature, and we've copied it in our technologies to make the same thing.
And what's amazing is that some people, especially some women, can actually see 4 colors. They have a mutation in their eye such that they can see more than just the 3 primary colors that most people can see. They can actually see 4 colors.
I was just thinking it would be interesting to look through somebody else's eyes. Of course, it's kind of impossible to do that without some rather gruesome transplants. But I wonder what that would look like, to see more colors than I currently see.
Science Fantastic with Professor Michio Kaku. With us today is Russ Swan, author of a new book. It's called The Physics Behind... ... Well, before the break, we were talking about lasers, rainbows, and now let's talk about stealth bombers and another form of electromagnetic radiation. And are they really invisible? So, Russ, tell us about stealth bombers.
Well, stealth bombers, of course, are designed in a few different clever engineering ways to minimize their radar reflection. So they're not invisible to natural light. You could see them. They're not really quite invisible to radar, but they're almost invisible to radar. And there are probably 2 main methods that are used to reduce the radar signature. One is the shape of things. So if a radio signal is transmitted from a radar station, if it is something made of metal, it will bounce back. And if you make the thing that it's bouncing off of made of lots of flat surfaces, then instead of coming back towards the radar system, they might reflect off into a different direction so they cannot be detected. And that immediately reduces the radar signature of, for instance, the aircraft. It also applies to warships. Retroreflectivity is one of the interesting things here. If you're wearing a high visibility garment and you notice it when you shine a light on it, it shines back very brightly. That's because they are designed specifically to be retroreflective, not just reflective, but to reflect the signal back the way it came. And a stealth bomber is designed for the exact opposite purpose, to be completely non-retroreflective. So this means that when they design the aircraft, they have no right angle, because a right angle allows an energy beam to bounce once, bounce twice, and come back the way it came. So if you look at a stealth bomber, you'll see that there's not a right angle to be seen almost anywhere. The other thing that they do, of course, is the surface treatment. They paint them in a radar-absorbing material. Basically, it's black paint, you might say. And that paint absorbs the signal, and the arrangement, the geometry of the thing, stops it being reflected. And that means that altogether you could have something as big as a bomber that has a radar signal about the same as a bird or a bumblebee. Really very tiny.
Okay, well, of course, course, the average person has seen movies like Harry Potter, where there is an invisibility cloak, where you really, really, really are invisible to light. Now, there are some things called metamaterials which give you a semblance of invisibility for microwave radiation. But, well, what are your thoughts about one day whether or not we're going to create true invisibility with metamaterials for optical frequencies, or is that just Harry Potter?
Well, it's a fascinating idea, isn't it? These metamaterials, what they say they do, what they promise is they will take an incoming light signal. Say there's light coming in from behind you, and it will hit the coat you're wearing, or the invisibility cloak, travel round the cloak, and then continue towards the viewer.
Welcome back to Science Fantastic with Professor Michio Kaku. Our special guest today is Russ Swan, author of the book, The Physics Behind... ... Well, let's move on now, and, well, let's talk about the moon. The moon is in our dreams. We see the moon every night, or most nights, but people wonder, well, where did the moon come from? And we're going back to the moon. The President of the United States has announced that, yes, we are going back to the moon. NASA is no longer going to be the agency to nowhere. It's going to go someplace. But let's say a few things about the moon, like, where did it come from?
It's a really interesting question, and I think it's fair to say that a lot of scientists are still not entirely sure. The main theory at the moment seems to be that the proto-Earth, the young, red-hot planet that became our Earth, had a catastrophic impact with another body in the solar system, something about the size of Mars, we think. And the two merged together in this huge molten lava mess. And as they spun and cooled, a lot of the material came off the Earth, and that became the moon. The mathematics, the arithmetic, seems to show that is about right. But there's still some anomalies. If we look at what we see on the Earth and what we see on the moon, they're not exactly the same. They're made of slightly different material in some places, and that is still proving that we need to go really back to the moon and do more science, because it's only by going places and making investigations that we really find out what the universe is all about. We still don't know a lot, and that's very exciting, I think.
Now, isn't it true that most of what we know about the moon's origin comes from the Apollo space program, when astronauts brought back hundreds of pounds of moon rock? What are your thoughts?
Well, that's exactly right. Most of the lunar material we have on Earth came from Apollo. There are a few small pieces that came actually directly from the moon by a meteor hitting the moon, knocking off a chunk of moon rock which floated around in space for perhaps thousands of years before traveling to Earth, plunging through the atmosphere, and eventually being picked up by some curious human. So most of what we know from the moon comes from Apollo, and the thing about Apollo is that most of the samples that came from Apollo are from the same kind of terrain. They're from the sort of lowland areas, because that's where it was possible to land an Apollo spaceship. The lunar excursion module, the LEM, wasn't really capable of landing on the side of a mountain. So we don't really know what the chemistry of all the lunar highlands is like. We can do some investigation from Earth. We can test it remotely by things like spectroscopy. But there's nothing quite like having a piece of the rock in your hand and being able to hit it with a hammer and look at it under a microscope to find out really what it's made of. It's a good idea to go back.
Yeah, in fact, I did that when I was a grad student years ago at Berkeley. I actually had some moon rocks from Apollo, looked at it under a microscope, and I was rather astounded to see tiny micro craters, because, of course, there's no air on the moon to burn up meteors. And inside these micro craters were tinier craters, craters inside craters inside craters. Amazing, because there's no air on the moon to burn up these particles of meteorites from outer space. Science Fantastic with Professor Michio Kaku. Today, we're talking about the physics behind with Russ Swan. So, Russ, where we last left off, we were talking about how do we determine how old things are. For example, how do we know when the dinosaurs died?
Well, indeed, the radiocarbon dating uses an element carbon-14, which is an isotope of carbon, which has a radioactive property to it, and it, like all radioactive things, it will decay, which means it becomes a bit less radioactive over time. And the joy of the physics behind this is that the pattern of the radioactive decay is very mathematical, it's entirely predictable, and if we can measure a sample of the carbon-14 and see how radioactive it is now, it's quite a simple matter to then go back and say, well, this means that this piece of carbon-14 was captured X years ago. It may be 2,000 years ago, it may be 20,000 years ago. But it's really, really useful, particularly for organic things, things that have once been alive, so a piece of bone or whatever. It absorbs carbon from the atmosphere, and the carbon-14 is made in the atmosphere by cosmic rays and then floats around in the air, gets absorbed by the living creature. When the living creature dies, the radiocarbon begins to decay, and a few thousand years later, an archaeologist comes along using the physics of radioactive decay, does a quick measurement, or not technically quick measurement, it's quite a complicated measurement, but it's very accurate, to determine whether something is 10,000 years or 100,000 years old. It's fantastic.
And isn't it true that we have not just one clock, but many clocks, that is, many radioactive substances that decay at different rates, plus DNA. We can actually compute how old things are by looking at their DNA, because DNA mutates at a constant rate over long periods of time. So isn't it true that we have many clocks, and all these clocks agree with each other, so we're not making a mistake?
Well, that's right. Radiocarbon is particularly useful for things that are perhaps between 1,000 and 30,000 years old. But we use things like potassium-40, which has a life of 1.25 billion years. Or we use rubidium-87 and strontium-87, which have a half-life of around about 50 million years. So by using 50 billion, I beg your pardon. By using these, as you call them, various clocks, and we call them clocks in rocks in terms of archaeological dating, we can come up with a picture of things. We can also cross-reference. So, for instance, if we have a sample from, say, an Egyptian pyramid, there's quite good written evidence of when that happened. You can then do the carbon dating, and it agrees with the dates of the history. So then it's another confirmation that we know exactly when things happened. And it proves that, the Earth is not 7,000 years old, it's 4 and a bit billion years old.
Okay, and now let's talk about the age of the universe itself. And people wonder, how do we know how old the universe is? First of all, tell us a little bit about the Doppler shift and the expanding universe, and how we determine how old the entire universe is.
Yes, well, I think some of the greatest scientific discoveries, really, of the 20th century were that the universe is expanding. First of all, it was considered that the universe was probably static, things were moving about a bit, but the discovery by Edwin Hubble, really, that things were moving away from each other and everything was moving away from everything else, was one of the big, big breakthroughs of science in the 20th century. And one of the bigger discoveries more recently was that not only are things moving away from each other, but they're accelerating as they move away. And this is really quite hard to get your head around. It doesn't seem logical that they can be expanding and accelerating expansion in the universe, and yet this is what the physics shows us. It's another proof, really, of the philosophy that we have to go looking for things, and you will find things that you didn't expect to find. Doppler shift is one of the most powerful things, of course. As a star moves away from us as the observer, its colors appear to change, not unlike the way that the colors in a rainbow will change as you move your position. So if a star is moving away from us, it looks a bit redder than it would otherwise. The red shift can then be used to measure how far that star is away, because the further it is away, the faster it's moving. And the Big Bang Theory puts all of this into reverse if we look at all the stars and all the galaxies in the universe and see the way they're traveling today, and then run that clock backwards. years ago, when they must have all been in just about exactly the same place.
Okay, Russ, unfortunately, we have run out of time for Science Fantastic. But thank you so much for coming on the air and talking about your latest book, The Physics Behind. Thank you so much.
Well, thank you. It's been an absolute pleasure.